I can share. Hi, sir. We are just waiting for Shayan to join. Just give us 2 minutes. We are really sorry.
Okay, good evening, everyone. Hi, Amit. I think our chair is
hi.
Yeah.
Yeah.
Our chair Shayan is not yet here.
No problem.
We sent him an email. So, so let me welcome Amit and all of you to this session. And as most of you perhaps know, Amit is a professor at IIT Delhi, and his area of interest is quite varied in theoretical computer science, from online algorithms, approximation algorithms, combinatorial optimization. And if I was seeing his Wikipedia entry, I think he would be maybe the first person in algorithms to get the Shanti Swarup Bhatnagar Award in 2018. And I think that forebodes well for the community. So, yeah, with that, I hand it over to Amit for his talk today on online caching. Over to you.
Thank you, Vikram. Thanks for joining. I know it's late evening, so I'll try to keep it light. I don't have slides, so I will write on my tablet. Hopefully, that will slow me down also. And please feel free to interrupt and ask questions. So this is about online caching. Let me just try to share my screen. Okay, so can you see this?
Yes. Yes, please.
Okay, great. Thanks so much. So, okay, so I'm going to talk about online caching. So I can't see the Zoom video, so please just speak rather than type something, so it'll be easier. So I want to talk about this online algorithms, and in particular online caching. And I don't know if people are familiar with online algorithms, so I'll spend maybe 5-10 minutes just setting up telling you the basic setup. And then I'll talk about online caching problem in particular, although the ideas here have been used in other online algorithms also. So hopefully you will get a sense of the kind of techniques people use. I won't get into all the technical details, but I hope to give you enough sort of ideas so that you can go back and read the papers. Also, today will be just like basic traditional algorithms and things which are known, which were done in the early 90s or in early 2000s. And next time we'll talk about more recent results in this area. Okay, so let me begin by just talking about online algorithms. Uh, Although the setup or the examples that I will use will be from caching. So in general, if you we've been looking at I guess polynomial time algorithms, and there the setting is that the input is given, and so there the input is given as a just one second. So for some reason, just one second. This was working fine last time.
No problem.
So yesterday we checked this was fine. So this, just give me a second. Otherwise, I'll just write with my finger if there's an issue with the pen. Usually, it never gives an issue.
So black is working. You want to change color?
No, I see my finger is working. I don't know why the pen is not working.
Is it the battery?
No, the battery was okay when I. Maybe it is. No, so something is wrong with the pencil because it should have shown the charts. Let me write with my finger and let's see. We know online caching where online algorithms. What happens is that the input arrives over time. Okay, so normally when you're given a problem, the input the entire input is specified to you, but in online algorithms the input is not specified to you. Okay, so what happens is the input arrives over time. Okay, so think of again, let's look at the caching problem. So what happens is that you are given some sort of a cache. Okay, and think of a cache as something which can hold up to, let's say, k pages. Okay, so this can hold up to k pages, and what's happening is that at each time a page request arrives. Okay, so the input consists of, let's say, sigma 1 is you want to see page 1, some other page sigma 2, sigma 3, and so on. Okay, so over time these page requests arrive, and the idea is that this cache can only hold up to k pages. So if the page is in the cache, then no cache miss happens. But if the page is not in the cache, then cache miss will happen, and you will have to sort of evict a page and bring in the requested page. Okay, so each time you evict a page, then you pay some sort of a cost that you think of. Let's say you're trying to minimize the number of evictions, and so the idea is to have a cache replacement policy or a cache eviction policy, which minimizes the total number of evictions. Okay, so this is the basic setup. This is the kind of problem we are going to talk about, and okay. And the reason why it is online is because you don't know the entire page sequence request in advance. Okay, so if I knew that, then this would be an offline problem, right? So suppose I told you that look, sigma 1, sigma 2 up to sigma n is the entire sequence of pages, and figure out a cache replacement policy which minimizes the number of cache misses. That's an algorithm that you study in algorithms class. And the algorithm which gives you the least number of cache misses, this is like farthest in future. So you look at so whenever a page request arrives and this page P is not in your cache, what you do is you look at all the pages that are there in your cache, and you see the one which will be requested farthest in the future, okay, among all those ones. And that's the one you sort of evict from the cache, okay? And and this algorithm is known to be, it's not hard to prove that it is optimal, okay? But the problem that we are dealing with is an online problem where we don't know the sequence of page requests, okay? And and this is what we are more interested in, right? We don't worry about, I mean, traditionally when you talk about online algorithms, we don't even worry about the computational time. You could take, exponential time, although it would be good to have something which runs in polynomial time. But the main challenge is to, without knowing the future input, how do you figure out what to do at the current point of time? Okay. So, and and how do you measure how good an online algorithm is, right? So let's say in the setting of caching, so but this is true for any competitive, any online algorithm. So how do you sort of measure how good an online algorithm, right? So measure how good an algorithm is. Okay, so an online algorithm is, okay, and this is done by looking at by measuring the ratio of the cost incurred by this algorithm, and somebody who knew the entire sequence, what would be the cost incurred by that algorithm. Okay, so looking at the ratio of these two things. Okay, so okay, so this is called competitive ratio. So you look at the ratio of, so let's say you are given some input. Okay, so let's say the input is sigma 1 up to sigma n. Okay, and let's call this input I. So you look at the ratio of how much is the cost of the algorithm, okay, on the input I, okay, over the optimal solution over I. Optimal means something which knew the entire sequence sigma 1 up to sigma n. So this would be the farthest in future, and then you take the maximum over all inputs I. Okay, so in some sense you look at the worst case input where the algorithm is measure how bad this online algorithm performs, or what is the cost of this algorithm on that input, and take the ratio with respect to something which knows the entire input. Right. So this opt I would be need not be polynomial time algorithm. It's like given this input, it's the optimal solution from that. Okay. So we may not be able to even compute this efficiently, but that's what it is. And algorithm I is something which is the way it is behaving is that each time a page request comes, and it has to say whether I mean, if the page is in the cache, great, nothing happens. But if page is not in the cache, then it has to evict a page. Okay, and so here we are measuring the number of evictions. Okay, so number of evictions. Sorry. Okay, so here we are measuring the number of evictions. Okay. So that is the setup. Any questions here? Okay. So
sorry, one question. So the denominator is also measuring the number of evictions, is it?
Yes, denominator is also measuring the number of evictions. But alg is saying is how much is the algorithm, how many evictions the algorithm incurs, and opt I is like this farthest in future algorithm, right?
And what is the cost? You said cost.
Cost is essentially for us right now. The cost is just the number of evictions, but it could change depending on what problem you're looking at. Okay. But for us, it will be just the number of evictions. Right. Okay, good. So so let's look at and this is called this parameter is called the competitive ratio. Okay, so this is called competitive ratio of the algorithm.
In your case, do you know what is opt of I?
Well, opt of I for this particular problem would be, as I said, look at the farthest in future algorithm. It says that when you request a page, when the page P is requested and it is not in the cache, you look at that page in the cache which will be requested farthest in the future. Okay. So let's say this is some page P1, P2, and so on up to Pk. And for each of the, and this is your current input, and let's say this page P is requested at this time, and let's say P1 will be requested at this point of time, P3 here, maybe P2 here, and maybe P4 here. So at this moment you evict P3. Okay, because P3 is the one which will be requested at the very farthest in future. Okay? So that algorithm is known to be optimal. But this could be an NP hard problem, so it may not be possible to compute this efficiently. But still, we want to say something about it. Okay? And the point is, we don't know what the input is. Okay, I don't even know what this n is. So the algorithm doesn't know these things. So at time t, algorithm just sees sigma t, and it doesn't know what is sigma t plus 1 up to sigma n. So it doesn't know what is farthest in future. Okay. Right? Okay, great. So let's look at some examples. Okay, and so first example is where so let's say there are k plus 1 pages. Okay. By the way, so let me fix some notation. So k will always denote the capacity of the cache. Okay, and n will be the number of pages, total number of pages. Okay, so n would typically be much bigger than k. Okay, but let's say for us n is equal to k plus 1 right now. Okay, and a is some algorithm. Okay, for caching. Now, and the way to think about online algorithms is that you think of somebody who is looking at this algorithm A, and at each time, I will this, and somebody means, let's say there is an adversary. Okay, and this looks at what A is doing, and at each time it will give an input or give a page request, which will be very bad for A. Okay, so which will make A pay a lot. Okay, so let's see how this happens. So let's say A is currently holding some pages. Okay, it has a cache of size k, and what this and I'll give you an input sigma 2 up to sigma n as follows. Let me not use n. N is for the number of pages. So let me use sigma t here. Okay, so this goes on for t units of time, and the input is as follows. Okay, at time t, I will look at the page which is not in the cache, and I'll give a page request for that. Okay, so request for a page which is not in the cache. Okay, makes sense. And and if I do this, then the algorithm will, of course, incur a page miss, and it will have to bring a new page. Okay, so there is an adversary which is kind of looking at what A is doing, this algorithm is doing, and each time is giving me some sort of a worst case page for me. Okay, so if you really look at the cost of the algorithm, right? So if you think of this as the input, then my notation is alg of I is telling me how many evictions alg incurs, the algorithm incurs. This will be t. Okay. Okay. Fine, because at each time now, what is the optimum for this input? I claim that it is t over k, and the reason is that if you think of the optimum solution, this farthest in future algorithm, it is storing some set of k pages, and when a new page is, let's say a page is requested which is not in the cache. Okay, now which page will I evict? I will evict the page which is among these k pages will be requested farthest in the future. So in the next k minus 1 time steps, I will not incur a cache miss. Okay, so maybe to k minus 1 here. Why will I not incur a cache miss? Because in the next k minus 1 steps, the pages that will be requested will be in my cache, because I explicitly knew what pages would be requested in the future, and I would evict that one which will be at least k steps away. Okay, so optimum will be like t over, I think it's t over k or t over k minus 1, and so if you look at the ratio of these two things, so this implies that competitive ratio of I, right? So competitive ratio of the algorithm, right, is at least k, because all I have given you is an input where the ratio is k. It could be worse for some other input, right? I don't know if for some other n or for some other k. Okay. In fact, this is true for any online algorithm here, because I didn't use any property of the algorithm, right? So what we have shown is that if you think of any online algorithm for caching, right, its competitive ratio will be at least k. So the ratio of how much evictions it can incur with respect to the optimal will always be at least k. And this is a very simple example, right? Any questions so far? Great. So now, okay. So now several questions arise. One question which arises is there an algorithm whose competitive ratio is at most k, no matter what n is? Okay. So in this particular case, n was exactly equal to k plus one. But so in general, right? So question is in general, can I have an algorithm with? Can we always achieve? Can we achieve this competitive ratio to be at most k? Right? Can we achieve competitive ratio to be less than equal to k, right? So that's the first question, right? Um, right, and second question is, now this may seem very pessimistic, right? Because it's saying that if you have a cache of size 100, you will be factor 100 off, and there's nothing you can do about it. And this very simple example shows that in practice this doesn't happen because, of course, there is some locality of reference and all that, but we're not looking at those things, right? The second question that we want to ask is, does randomization help? Okay, so right now the algorithm A is a deterministic algorithm, but can I do better if I am allowed to toss coins? Because then the adversary will not exactly know how my algorithm is going to behave. Okay, so of course, if I use randomization, I have to define what is the meaning of competitive ratio, which I will do in a minute. But so let me say what the answers are. First answer is that yes, so there is an algorithm which has competitive ratio of at most k. So in some sense, this k is the right competitive ratio. And but if you allow me randomization, I can get a competitive ratio of log of k. Okay, so there's a huge improvement from k to log k here. Okay? And that theme runs through the entire area of online algorithms, that in some sense, if you allow me randomization, I can do much better. And the reason is that if you allow me randomization, somebody who's trying to design a worst case input for me would not know how I will behave. So there's a limitation of how bad things can get for me. Okay, so that's why you often see a huge improvement when randomization is allowed. Any questions? Okay, so let me show you both of these things quickly, and then I will go over what other problems people consider here and what are the techniques here. Okay. All right, so let me show you how to achieve right. So an algorithm which achieves uh, competitive ratio of k. Okay, and if you have ever done a course in algorithms, oh sorry, not in algorithm, in hardware, people talk about this algorithm called LRU. It's called the least recently used algorithm. And it says that, look, I don't know what the future is, but I know what the past is. So I will look at some sort of past behavior and evict a page which has not been accessed too often. Okay, in some sense, which so look at the version that I'm going to describe, it's called 1-bit LRU, and you can have 2-bit LRU and all that. But even like a very simple 1-bit LRU algorithm, as I will show you, has competitive ratio of only k. Okay, so what is this algorithm? So think of this algorithm as going in phases. Okay, and this bit means that if I have a cache and it has k pages, I have a bit for each page in the cache. I'm going to either mark it or I'm going to unmark it. Okay, so think of putting a tick mark means that I have marked it. Okay, so each page will be either marked or unmarked. Okay, now at the beginning, every page is unmarked. Okay, so you begin a phase by saying that initially, so let's say there's some initial state of the cache. I don't care what pages I have in the cache, but initially all pages are unmarked. Okay, so initially all pages unmarked. Okay, actually, let me just not use the word phases right now, and I'll come back to phases later. So initially all pages are unmarked. Okay, and let's say at time t, let's say you request a page, pt is requested. Okay, now several cases can happen. Suppose pt is in the cache, right? So then you kind of mark it. You say that, look, this page pt has been requested, So let's mark it and let's not evict it if I need to evict the page, okay? Because it has been accessed recently. Okay, so you just mark this page. Second option is that PT is not in the cache. Okay, this is where the algorithm is going to incur a cost. Okay, right? So if PT is not in the cache, what you do is there are two options. One option is that suppose now the question is, which page do you move out from the cache? Okay, so you say that let me remove an unmarked page from the cache. Okay, or evict. Let me use the word evict. So you evict an unmarked page. Okay. Okay, and you bring in PT in the cache and you mark it. Okay, makes sense? And now the only thing is that what if all the pages in the cache are marked, right? So what is this unmarked mark doing, right? This mark is essentially saying that this page has been recently accessed. Okay, so if you're unmarked, it means that you have not been recently accessed. So if you have to remove somebody, you remove a page which has not been recently accessed. Okay. Now the only issue with this whole algorithm is that what if all the pages are marked, right? So what if all pages are unmarked, are unmarked? Okay. So in this case, what you do is you sort of reset the whole thing. You say that let me reset. So mark all the pages, unmark all the pages. Okay, sorry. So in some sense, you're going to reset everything. You unmark all the pages, and essentially what you will do is you'll just pick any one of them and you will remove it and bring in PT. You will mark it, and this whole process goes on. Okay. Any questions here? Is that okay? So I assume the algorithm is clear, right? So it is the standard LRU algorithm. And why is it called 1-bit LRU? Because you're just using 1 bit to keep track of whether the page P was accessed recently or not. What's a 2-bit LRU? 2-bit LRU would be where you have 2 bits, and these 2 bits kind of count how often this page has been accessed recently. And if you have to remove somebody, then you remove the one among the marked ones which have been whose counter is small, which haven't been accessed too often recently. But even 1-bit LRU is good enough for us. Okay. So let's quickly analyze this and see why. Yeah. Go on, please.
Would it not be what if all pages are marked?
Yeah. So if all pages are marked, then you unmark all the pages. Yeah.
Okay. Thank you.
Yeah. So I think if they are all marked here. Yeah. Okay. So let me try to analyze this quickly. And the way to think about is you break down the input into, there are times at which you execute this unmarking operation, right? So let's call this as a phase, right? So each time you unmark all the pages, let's call this as beginning of a new phase, okay? So a phase happens when initially you start at time t equals 0, and the phase will end when all the pages have been marked and a new page is requested, which is not in the cache, in which case, you will again start with all pages being unmarked here, right? So all pages unmarked. So a phase is essentially when it starts when you have all the pages as unmarked, okay? So a phase starts, a new phase starts when all the pages are unmarked. Okay, so when all pages are unmarked. Okay, and actually this phase has nothing to do with the algorithm. When will a phase start? When a new phase start? When during a phase, you will only sort of access the pages which are yeah. So okay, so let me not do that right now and come back to that. Okay, so now how many cache misses will happen in a phase, right? So during a phase, I claim that during a phase at most, in fact, exactly, the algorithm incurs exactly k cache misses. Why? because each time, let's say some page P is accessed here, each time this page and this a page P could be accessed many times during the phase, right? Each time, the first time this page P is accessed, there could be a cache miss. This page is not in the cache. But after you access P, once you access P, this page P gets marked in my cache. Okay, and so for all subsequent accesses, for all of these accesses, it will never get evicted again. Why? Because each subsequent access to this page P will be marked, and so so it cannot be evicted, because by policy you have to evict only an unmarked page. And I will always have an unmarked page because that's the definition of my page. I mean, this is the next time when everything is getting unmarked. So prior to that, you will always have somebody who will be unmarked. Okay, right? And
so why exactly K?
Oh, at most K, because this page P could have been in my cache already.
Okay.
Yeah, so, right. You're right. Okay, so so now this shows that the number of cache misses, right? So number of cache misses, right, is at most K times the number of phases. Okay, and what about the optimum algorithm, right? What about the algorithm which knows everything? I claim that it has to incur at least, if there are, in each phase, for each phase it has to sort of incur at least one cache miss. Why? Because what happens at the beginning of a phase? At the beginning of a phase, all the pages are unmarked. Now, to mark all of those pages, you have to at least request each such page at least once, right? So during a phase, you will request at least K pages, or in fact, exactly K pages. And then at the end of the phase, when the next phase starts, you are requesting a new page which is not in the cache. Okay, so if you look at all the pages which are accessed during a phase, and at the beginning of the next phase, these are K plus 1 pages, right? So so during a phase, K plus 1 pages are accessed. If I also count the starting time of the next phase are accessed, and so there must be at least one cache miss. Okay, so this shows that this proves that any algorithm, right? So cost of, even if somebody knows the entire input, right? Any algorithm has to be at least a number of phases. Okay, and so if you now compare these two things, you realize that the ratio is K, and so this shows that this algorithm has a competitive ratio of K. Okay, so far so good. Okay, good. Now, so that shows that this simple marking algorithm incurs a competitive ratio of K, right? So that answers this question. Now, let's look at the next question. That does randomization help? Okay, and
Amit, I think there's a question on chat. Sorry to interrupt.
Can you just say what it is?
Yeah, so Venkatesh is asking what happens
see,
for 2-bit LRU.
Yeah, so the point is that 2-bit LRU does not help at least in the competitive ratio, because the 2-bit LRU does not help because we just showed that no matter what you do, right, you can use any number of bits LRU. I have a very simple algorithm or input which shows that you cannot improve on K. And what this is saying is that even with 1-bit LRU, I can get a ratio of K. And so that's tight, because I really having 2 bits or 3 bits, at least for the this competitive analysis here, does not help. In practice, it does help because you can you will not get this kind of worst case input here. So in practice, it may help, but at least for our analysis, it does not help at all. Right? You can't go below K, and already 1-bit LRU is giving you K. Okay. So in that sense, this is not is somewhat pessimistic in the sense that you are getting the tight lower bound even with 1-bit LRU. I mean, that's good and bad in the sense that any further, I don't know how to design better algorithms as if this is a framework I'm in. Okay. So let's now look at the randomization. Will randomization help? And what is a randomized? Okay, so let me just say what the setup is. So suppose my algorithm A can now have can toss coin. Okay, so suppose algorithm A is now a randomized algorithm. Okay, so now if given an input sigma 1 up to sigma n, of course, again, the algorithm does not know what the input is. But now I can talk about on an input I, the expected cost of the algorithm, right? So expectation of algorithm, let's say on the input I. Okay, so what does this mean? It means that this is the algorithm it's a randomized algorithm, and on this input it will have some expected number of cache misses. Okay, and it depends on the coin tosses of this algorithm. Okay, and again I divide this by the optimum on the. Okay, so okay, and this is called the expected competitive ratio, right, on I. Okay, so expected competitive ratio on I. And again, you can ask, like, how bad this can, or how good this ratio can be. Okay, right now. Okay, good. Now, I won't get into this, but it can be shown that, and if you know what Yau's lemma is, then you can use Yau's lemma. And using Yau's lemma, one can show that this ratio, the expected competitive ratio of any algorithm, okay, for online caching, has to be at least log of k. Okay, so just like we had this adversary, which could give a bad example for us. There would be okay. So now there is an adversary, but then this adversary doesn't get to see the coin tosses of the algorithm, and so this lower bound goes down from k to log k. Okay, so you cannot get a constant, but at least it says that you cannot go below log k. Now, but what we will show is that there is a very simple algorithm which achieves a expected competitive ratio of log of k. Okay, so I hope the definition is clear, right? So nothing happening, but just that instead of looking at the cost of the algorithm, we look at just the expected cost. Okay, and then you just again take the supremum over all possible inputs. So that would be the
for some algorithm, if we know the expected competitive ratio, so can we say something about the competitive ratio in general?
No, I mean the two things. If the algorithm is a randomized algorithm, for the deterministic one, that will it be at most some exponential or something? No, we don't. I don't know any such connection. Yeah, I don't think you can say anything. Yeah, I don't think so.
Amit, I just want to clarify one thing.
Yeah.
So suppose I am still in the randomized setting, but now adversary is a bit more powerful. So let's say it can actually see the outcome of your random tosses.
Yeah, then the
Okay.
same example that I showed you will give you a k, right? I mean, then randomization does not help. So this is called an oblivious adversary where it doesn't see your coin tosses. Only then you will get a log k. Otherwise, we're back to the same situation. At least for this example.
In general,
In general, it could help. No, it can help. So there are settings.
Okay.
There are two kind of adversary people look at: oblivious and non-oblivious. I am talking about oblivious only. In this context, you have to look at oblivious. Otherwise, again, the same example that I showed you will give a k. Yeah, but in general, it's not true. Sometimes it can help. Yeah, even if okay. Okay. Good. So what is the algorithm? The algorithm is essentially the same 1-bit LRU algorithm. But all I will change is I'll say that when you're trying to evict, here in this step here, I said that evict any unmarked page. But now the only, it didn't matter if there were several choices here, it didn't matter which page you were evicting. So the only change I'll make is that you evict a randomized. Okay, so you randomly pick an unmarked page. Okay, so randomly chosen. Okay, unmarked page. So if there are several choices here, you pick a random. Okay, and that's the randomized algorithm. Okay, and I want to prove that its expected competitive ratio is at most log k. So is the setting clear? I hope the algorithm is clear, right? Not much happening. So let me sort of give you an outline of the proof. I don't want to spend too much time on it because anyway we'll look at other more modern techniques. So the outline of the proof is essentially that you again have these phases. Okay. Now, if you really go back to the earlier definition of a phase, it seems that the definition of a phase depends on how the algorithm is behaving. Because we are saying that a phase starts when all the pages are unmarked. But if you think a little bit about it, actually it doesn't matter doesn't depend on the algorithm. A phase will end when you have requested exactly k plus 1 distinct pages, right? So in fact, this definition of a phase is independent of the algorithm. So each time you are requesting k plus 1 distinct pages, the moment you request the k plus 1th page, that's when a new phase will start. Because the previous k pages will be all marked, they will be in your cache, and when you look at the next a new k plus 1th page, that's when your phase will start. So this notion of phase actually doesn't depend on the algorithm. It's a property of the input. So again, you can talk about phases. Okay. So far so good. So let's say this is some phase I, this is phase I minus 1, and during this time there is something in the cache. Okay, some pages in the cache, right? So there are some k pages which are there in the cache, and they're all unmarked to begin with. And now during this phase, there can be two kind of page requests. There will be some page requests which are already in the cache. So I'll call them as old page requests. Okay, or rather, let me use the word stale page. Okay. So these will be stale requests. What is a stale request? It's a request for a page P which is already in the cache at this moment. When let's say at time t when your phase started. Okay, and the second kind of request will be like a new page request. It's a page request which is not in the cache. Okay, a new page request. Now, note that a page P could be again accessed multiple times. So, but all of them will be called a stale request. Okay, because this page was already in your cache. Okay, and a new page request is something which is not in the cache at time t. Okay, so there is some page q requested here. Same page q can again be requested again and again. But again, it's easy to see that the first time it is accessed, that's the only time you have to worry about this page, because the first time you access it, you mark it, and then you will never ever evict it during a phase. Okay. So let's give them some names. So this is Si, and this is, let's call it Ni. So if you look at the distinct pages, Si plus Ni will be equal to K, because during a phase you will see exactly K distinct page requests. Okay. Now each of these Ni's will cause a cache miss, because this is not in your cache to begin with. So in a phase you will definitely incur Ni. Okay. The question is really, for these guys, will I get a cache miss or not? Okay. Right, because let's say this page P, let's say at this moment you request. So let's take a simple example where let's say all the new pages, let's say Q1, Q2, they are accessed first, and then you access some of these stale ones. Okay, let's say some page P is accessed, which is a stale page, which was there in your cache. So what's the probability that page P will when you access this page P, there is a cache miss? Okay, and it depends what you did during these Q1 up to Qni. Okay, so for example, for each of these Q1, Q2 up to Qni, you will evict a random page from K, which is basically a random page from this cache, because all of them are unmarked and none of them are getting marked. So when this page P is accessed, the probability that it is not there in your cache, that is this cache miss happens, is exactly Ni over K, right? That makes sense? Because this will only happen if you had evicted page P. Okay, and similarly, when if you look at the next stale page request, and this is something that you can do, the probability that it is not there in the cache when P prime is accessed is again Ni over K minus 1, because you kind of ignore P and look at the other pages. They're all in some sense equivalent, so you will get Ni over K minus 1. Okay, and so on. Okay, so right. So if you do this calculation, this turns out to be at most Ni plus Ni times the harmonic series for K. So log K. So roughly Ni log K. So this is the expected number of cache misses during a phase, right? This is where I'm using the randomization property, right? So expected number of cache misses. I should say Ni plus 1 because Ni could be 0, but ignoring that. Okay. And what about the is this point clear? How I get an log k? And so you the total number of expected cache misses is summation over I 1 plus ni times log k. This is the total number of expected cache misses by the algorithm. Okay. And what about the optimum algorithm? Well, if you look at two consecutive phases, right? So let's look at two consecutive phases, right? So phase I minus 1 and phase I. What can I say about the right? What is the total number of distinct pages accessed during these two phases? Okay, so total number of pages accessed during phase I and phase I plus 1. During this phase, you accessed k pages, which are there in your cache here, right? But then you also access some new pages here, so it's k plus ni. Correct? Because these k pages were there in, this is the state of your cache at the beginning of phase I, and then this ni is exactly those pages which are not in your cache. So it's k plus ni, which means that any algorithm, no matter what that algorithm is, even if it knows the input, if you combine phase I and phase I minus 1 and phase I, it will incur at least ni cache misses, right? Okay, right. So this is the main observation that if you look at phase I minus 1 and I, any algorithm will have at least ni cache misses. Okay, so then you look at phase I plus 1 and I plus 2, then you say that any algorithm will have at least ni plus 2 cache misses, okay, and so on. Right, so if you add them up, what are we saying? It's saying that you will have n1 plus n3 plus n5 and so on. So any algorithm needs to have at least these many cache misses. And again, by the same logic, I can say that any algorithm must have at least n2 plus n4 plus n6 and so on cache misses. And if you add them up, you say that any algorithm must have at least half of n1 plus n2 plus n3 and so on, right? These many cache misses. Okay, so that's the story for any algorithm, even if it knows the input. And if you look at this expression here, it says that the expected number of cache misses, if I ignore this one here, you can take care of this factor also. It is summation ni times log k. So now if you compare the two things, you see that the expected competitive ratio of this algorithm is at most like some constant times log k. Okay, so what we conclude is that the expected competitive ratio, right? So sorry, expected competitive ratio is at most big O of log k. Okay, and that's it. So this shows that the randomization helps here.
So I have a question. So you showed without any randomness, like zero random bits, you have hardness of k, and in this case, you have log k amount of randomness, and you're getting log k. So what is happening in the intermediate stage? Is it a smooth transition? Let's say I have 3 bits of random bits, or it's a phase transition that you need at least k minus k bits, log k bits to really get this.
That's a very good question. I don't know actually. That's a very good question. So how does it vary with the amount of randomness that I'm allowed? That's a very good question. I don't know if it is known actually. So that's a good question. I don't know actually. Yeah, that's a very good question. Actually. Yeah.
And another question, as you said, the hardness is log k, but it's like in the adversarial order. But if you, let's say, have random order, then is something known that hardness is much better, or
right. So in random order also, I think right. Actually, yeah, in the random order also, I believe it should be log k, because yeah.
Maybe deterministic will also have hardness of log k, I guess, but
deterministic will definitely have hardness of log k, because this what is the input which shows log k hardness? It's just like take some k plus 1 pages, and each time you show me a randomly chosen page. Okay, and you can show that any deterministic algorithm will have at least log k competitive ratio here. Okay, and I believe then this shows right in the random order. Well, it's not really random order. Yeah, I would believe it should be log K still. Yeah. 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 But people have studied other models as well here. People have studied sort of some sort of Markov chain models here. For example, you have input where, if this is the current page, the chances of seeing the same page next time is given by some Markov chain, right? So can you do better there? And I think some better results are known there. So you can get around this hardness of K by various ways. Yeah. Yeah. But you're right. In random order model, I think I have to check, but I think you can get log K, but I don't think you can go below log K. But I'll check this next time. Okay.
One
good.
more quick question.
Yeah,
Like, so,
please. Yeah.
so beyond Markov, can you use some get some high probability bound as well? That no, right?
Oh, is it close to log K with very high probability?
Yeah. So that
well, of course, you can use Markov, but so let's see what you're saying is, can I know? Well, yeah. So let's. Yeah,
maybe
I don't know this. Yeah, I don't think. At least for this, the input that. Okay, so let's see if it follows from here. It may just follow from here. That it may follow from just this kind of analysis. I think. Yeah. So you can. It may be possible to show that you get some sort of concentration. Should be possible to show. Yeah. But yeah. I mean, normally when people talk about competitive ratio, they don't. They just look at the expectation. They don't look at. But I think just this kind of harmonic series, it may be possible to show that chance that you go to 2 ni log K should be very small. There should be some concentration here. Yeah.
Okay.
Yeah.
Thanks.
Yeah. Okay. All right. So let me now. Okay. So now question is, what next? So there are several sort of extensions that people look at. So first extension is what is called, and this is what I will talk about next time, weighted paging. Weight paging is where every page P has a weight WP. Okay. And right. And so, think of WP as, maybe the size of the page or how important this page P is. And so when a cache miss occurs, you don't just count the number of cache misses, but you, for each cache, if a page P is evicted, you count WP for that. Okay. So you want to minimize the total weighted cache miss. Okay, so think of if page WP is the size of the page in some sense, like how much time or cost it will incur to sort of move this page out or move this page in. So although, by the way, I talked about cache misses, but you can also talk about the number of times you have to bring in a page, right? Or a cache miss is same as the number of times you move out a page is roughly the same as the number of times you move in a page. Both are roughly same. So anyway, so if page P is evicted, you don't pay 1, but you count WP. Okay, and now you want to minimize the total number of total weighted cache miss. Okay. This is called weighted paging. Okay. I hope this is clear. Okay, so what is known here? So this was open for a long time till Bansal, Bukbinder, and Naur in 07, they gave a log K competitive. So the same result that we have for unweighted paging. That's called unweighted paging, the problem that we have been talking about. They gave a log K competitive algorithm here also. Okay, but these were new ideas, new techniques. So this is what I want to talk about next time. So this is called weighted paging. A more general version is called generalized paging. Or generalized caching. So now here a page P has two things. It has a size SP and a weight WP. Okay. Now normally you would think of size and weight as being more or less same, but let's think of them as two different quantities. Weight is telling me how much it it costs us to evict this page, right? So this is telling me again that this is telling me the cost of evicting a page, P. But then, you can always ask, like, why are we saying that we can only hold K pages? Because now these pages are not same. So instead of talking about K, we say that this cache is a capacity of B. Okay, so B is the capacity of the cache. And the idea is that if you look at the pages which are in the cache, their total sizes should not exceed B. Okay, so earlier we were saying that you can have only K pages in the cache. Now we are saying that the total sizes of all the pages, right? The total SP value of pages in the cache. Okay, this cannot exceed B. Okay, so this is called generalized paging. Definition is clear, right? Okay, and now what we know is now the same. So Bansal Bhupender Naur in 2008. They gave again. So by the way, this log K has to be a randomized algorithm, because we know that even for the simple unweighted, it is you cannot go below K if you're using a deterministic. So they gave a log square K algorithm. Okay, and this was let me see my reference. This was later improved to by several people. So by Adam Nishek, Shumaj, Englert, and Reke in 2018, they improved it to log K. Okay, so again, for this problem, we know a log K comparative algorithm. Okay, while we are at it, let me also mention some more extensions that we have wrote down. So, so you can talk about. These are problems which are more recent problems. You can talk about what is called elastic caching. Okay, so elastic caching is where the cache size can change. Okay, so right now we're assuming that the cache size is K, or in the generalized one there's a fixed cache. But what if I allow you to change the size of your cache? Okay, so the model here is the following: that so you can have some cache size KT, but there's some sort of cost that you have to pay. Okay, so there are two things. So one is, like, of course, you have to count the number of cache misses, right? So number of cache misses, that's what you want to minimize. But for every time T, you're allowed to, you can keep any cache, you can change your cache size. Okay, so if you are maintaining a cache size KT at time T, then you also pay a cost C of KT. Okay, so think of this as some sort of maintenance cost. So as you increase the size of your cache, this cost goes up. So you can have a larger cache, but at the expense of paying more of this sort of maintenance cost. Okay, this is a more general problem than the problem that we had been looking for. For example, if you have a fixed size of cache of size K, then you can think of the following cost function, that C of S is equal to 0 if S is less than equal to K, and it is infinity if S is bigger than K. Right? So this is saying that you're only allowed, this term here says that this goes away, and essentially all it says is that you cannot be having a cache of size more than K pages. And now it's back to the original problem where you just want to minimize the number of cache misses. But you could think of this more general version where and if you really, this motivation came from this cloud computing kind of setting where these you can actually rent a cache for varying amount of time, and while renting a cache, you can pay different amounts depending on how big a cache you're renting. So that's where the motivation is coming from, that now you can vary your cache size, but then you pay an extra additive term here. Okay, and for this problem, and again you can ask this for in the most general sort of generalized paging sense, and what we showed that here you can get a log n comparative algorithm, okay, for general cost functions here. Okay, so this was joint work with Anupam Gupta, Demalya Panigrahi, Ravi Shankar Krishnaswamy, and myself, and we showed that you can get a log n comparative algorithm here. So that's one extension I wanted to say. The second extension that we recently got, and just mention this, is you can talk about caching with delays. And again, the motivation comes from various applications. That is, suppose some PHP is requested at some time t. Now, in the usual caching setting, you have to bring this PHP in the cache at the current time. But in caching with delays, what happens is that I allow you to bring this. Let's say I give you a time window. Okay, so I give you a time window like this, and I tell you that this page has to be brought in the cache during sometime during this time window. Okay, so you don't have to bring the page in the cache right now. Maybe you bring this page in the cache at this point of time. Okay, but somewhere in during this time window. Okay, and why does it help? This helps because or why is this problem interesting? Because suppose this is another request for the same page, then you can satisfy both of these requests by just like bringing it once in the cache. Right? And again, you can ask the question that suppose I give you a cache of size k. What can you say about this problem? Okay, so again with Anupam and Malya, Panigrahi, and myself. I think this was 19, this was 20. We gave a logarithmic comparative algorithm for this. I just wanted to say some of the extensions that have happened on this. But tomorrow I'll focus on these two problems because the ideas here are very sort of powerful and have been applied in many other algorithms as well. In fact, even for other these extensions. And so I want to relate these problems to linear programming and things like that. Okay. So this is what I will do tomorrow. So let me stop here. Any questions? I'll take questions.
Thanks, Amit, for the great talk. And I should apologize. I mean, I thought that it is 1:30 p.m. my time, and I don't know how I feel that, but it's 12:30 my time. Sorry about that.
No problem.
Okay, so is there any questions? Actually, I have one question.
Sure.
What would be a natural problem in online algorithms where against adaptive adversary, there is a gap between deterministic and randomized algorithms?
Right. So I have to see. So what's the problem where adaptive means it can see, right? Your pointer says. Right. So I'll have to think of. Yeah, I mean most problems that I know of, right? Set cover and case server. People only talk about oblivious. Yeah, I mean I know that sometimes it will help. I guess. In the setting of caching, I can't see of the most natural.
Okay, because what I was thinking was, if you allow for recourse, then I can see that there might be a distinction.
Right.
But without any recourse, just in the classical competitive.
Right. I mean, recourse, of course, here doesn't make sense because if you evicted a page, then that decision is done, right? I can't go back and change that decision. So in the context of paging, I don't know if oblivious, if adaptive. I mean, if you can, I guess you need oblivious adversary here. That's what my feeling is. Yeah, I don't know of any result which looks at adaptive adversary in the paging setting. Yeah, because I mean these lower bounds kind of apply even for adaptive adversary. Yeah. So, yeah.
I see. Okay.
Not in the context of caching, but like learning with experts' advice, those settings you do see such gaps.
Oh yeah. There of course it will. Yeah, of course. Yeah. There you can see the coin toss as it doesn't matter. Yeah. Exactly.
In the deterministic setting, is there some kind of special sequences where the competitive ratio is less than k?
Yeah. So as I think Arindam had asked, where let's say there are these models which are called random order models. And what happens is that what you do is you fix the, let's say, the set of pages that will be requested, right? So you say that, let's say page P1 will be requested 10 times, P2 will be requested 5 times, and so on. And but then you present them in a random order. So this is called random order model. And this can be, this kind of random order model can be thought of for any online algorithm, right? That you fix, first of all, sigma 1, sigma 2 up to sigma n, but you don't present sigma 1 up to sigma n to the algorithm, but you present a random permutation of sigma 1 up to sigma n. And many times, random order model, you can do better than than sort of an adversarial order, because it's saying that the adversary is only picking the set of pages which will be requested, but then you are presenting them in a random order. So that often helps. So that's one setting. The other is, of course, if you talk to people in hardware, they'll say that even with very small 2-bit or 3-bit LRU, they can achieve a cache miss rate of less than 1%, 0.1% or something. So again, they're using the fact that there is some sort of locality of reference, that if a page P has been accessed, then the same page P will continue to be accessed, is likely to be accessed in the future. So you can build models like this where the input has some properties, maybe some probabilistic guarantees. And in those settings, one can show better results. Maybe I'll talk about these next time. But in general, I guess if you just talk about worst case inputs, then K is the best you can. Because if you're thinking of when deterministic can do better, then you have to. I mean, the special kind of inputs you want to design is where they have some probabilistic guarantees. Maybe they satisfies. Yes, they come from some distribution, and then maybe you will be able to say that.
Yes. Okay.
Okay.
Any other question? Okay. So thanks again, Amit, for the talk. And we will continue tomorrow at the same time.
Same time, right? Yeah. All right. I'll see you then tomorrow. Okay. All right.
Thank you.
Bye.